Okay. Okay, guys, so let's start. Week number 4, recitation number 3. Today we have a couple of talk. We talked about independence of random variables and independence of events and about random variables. Also, both of them are important topics. So let's start. Let's start from the reminder. I want to enlarge it a bit. Let's move it here. Oh, yes, it's a bit. So, a brief reminder, if you, let's say the two events A and B are independent, if the probability of their intersection equals product of their probabilities, or we can use the second definition, probability of A given B equals probability of A. Equals probability of A. So this is the definition of independence of two events. Okay. Pay attention. This notion of independence is it's not intuitive. If you ask somebody, even from probability, does these two events are independent, he needs to calculate this, check this statement, because in many cases, intuition about independence can be wrong. It's very important, okay? So if you want to know, to be sure that two events are independent, we need to check for these statements or these statements, yes, but don't use your intuition, because, okay, this is first thing. How can define independence of n events, mutual independence? Oh, in this case, we need to check more statements. We need to check that for every sub-collection from these sets, the probability of the intersection equals to the product of their probability. And pay attention, in this case, we need to check something about 2 power n minus 1 probably equalities. Yes, so if n equals 10, in worst case, we need to check 1000 equalities. Oh. And let's start from this exercise about dice. There are many exercises about cards, dice, or balls and pins. So this is one of them. We have two dice, and we define here two events. The sum is 7, and the second event is we get some result, some special result on the first die. Okay. And we want to prove that these two events are independent. Okay, we get 7 as a sum, and we have information about the result of the first die. These two events are independent. Okay. So the question is clear? No. Okay, let's see. Okay, probably. Okay, look. We define two events. A, the sum of the result is 7, and for every I from 1 to 6, we define bi, but the result on the first die is I. And now our goal is to prove that probability of A intersection bi equals to probability of A times probability bi for every I. Or it's enough to check the probability of A given bi equals to probability bi. Or we can check the probability of bi equals A, given A equals to probability of bi. It's enough to check every one of them. Yes.
Could you please switch the marker?
Yes, I write here because it's not a book. Yes. Let's write on the computer. It's new marker, but it's not a book. Yes. Okay, so let's try this film. Okay, just a moment. Okay. Let's see. Oh. Okay. Let's check that. Okay. Just a moment. Okay. Yes. So it's enough to check one of these equalities. Probability of A intersection BI equals probability of A times probability BI, or probability of A given BI equals the probability of A, or probability of BI equals A, or given A equals the probability BI. You don't need to check every one of them. You can choose one, probably the simplest one, and check it. And we need to check it for every I from 1 to 6. But pay attention, in this question, it's enough to check only one of them because the proof is the same for every number, from 1, from 2. So it's enough to check for only one of them. And by symmetry, our proof will correct for every I. It's clear? So let's return to our question. Okay, this question is a question of definitions. So let's try. Okay, what do you want to check? This equality or this one? Doesn't matter. First one or the second? Let's start from that. Okay. And let's choose some I. For simplicity, suppose I equals 1. Okay. So we want to check, or it's enough to check, that probability of A intersection B 1 equals probability of A times probability B1. A, what is the notion of A? Sum of results is 7. B1, we got on the first die 1. Okay. What is the probability that when you throw 2 dice, you will get on the first die 1? What's probability to get 1? 1/6. Yes, 1/6, yes. Probability that we will get 1 on the first die is 1/6. By the symmetry, yes? If you want to explain it by the symmetry. Our die is symmetric. Okay, so we finished with this guy. Now we want to find the probability that sum of results is 7. Okay, yes. Okay. Pay attention. We can solve this question in general or in particular case, in this special case. In general, we can write it in this statement. Probability of A equals sum for every I between 1 and 6 for every J such that J plus I equals 7. Probability when first die we will get I, BI, times probability on the second die we will get J. I don't know, CJ. Something like that. Yes. For every I from 1 to 6, for every J such that J plus I equals 7, probability of first result and probability of second result. But it's a complex term, it's messy, it's not nice. So we don't need one-size solution. Okay? The simple solution, and it's advice for you in general, if you can draw your sample space, draw it. Yes, express it. In this case, our sample space, we can express it as a table. Yes, we have 6 rows for the first result and 6 columns for the second result. For 2 dice, you almost everything you can draw all sample space. Yes, let's draw it. It's a simple case. Okay. First die, second die. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, probably you want to ask me what we need to do if we have more dice. Yes? What we can do if we have 3 dice or 4 dice or 5 dice. If we have more dice, we can draw such table. Yes. Yes, you're right. But in this case, we can use, for example, we can use generating function, very powerful tools from combinatorics. But let's don't talk about it today. Okay, so this is our sample space, yes? Yeah. And now in the table we can write anything, any function of these two results, but we won't write any function. The question is about the sum of results, yes? So let's write in this table sum of results. Okay. For example, in this square, 2. The sum of results is 2. 1 plus 1, it's a 2. Here, 1 plus 2, it's a 3. Okay, so we can fill the table. 4, 5, 6, 7, 7, 7, 7, 7, 7, 12, for example. Oh, make sense? Yeah, okay. And what is the probability that the sum of two results will be 7? Yes. It's not always, but in this case, yes. Yes. 6 divided by 36. Why is that? We have fair dice. Yes, our dice is symmetric, is fair. So by probability, by definition of symmetrical probabilities, probability of event A equals to ratio. Here we write the number of all events where we get 7, 6, divided by the size of the sample space 36. Okay. So 6 divided by 36, 1 over 6. It was simple, yes? Yeah. Okay. As I said previously, for 4 dice, 5 dice. And more, we need to use generating function or some more complicated tools. Okay, let's use. Let's solve this question. It's enough for today. Okay, so where are you? We found also this probability. Yes, it's 1 over 6. Just a moment. Okay. Oh. Now it's 1 over 6. It's 1 over 6. We need to find this fellow. What is the probability that we get simultaneously both many? The sum of results 7, and the result on the first die is 1. Okay, we want to find probability of intersection. In general, not in this question, but in general, it can be very hard to find probability intersection. It can be very hard. But in this question is not. Let's use our table again. Let's find here our event. The sum of results is 7. On the first die, we get 1. Where is it? Here? No. Here, no. Here, no. Here, no. Here. Yes? The result on first die is 1. And sum of results is 7. Is there a very additional result for intersection? Additional event? Only this one. Only this one. So this fellow is a intersection V1. Make sense? Okay, what is the probability of this event? 1 divided by 36. Yes, 1 over 36. Yeah. Okay. So probability of this fellow is 1 divided by 36. Okay, now we need to check this statement. It's equality or no? It is equality. Yes, it's equality. So A and B1 are independent. In similarly, A and B2 are independent, A and B3 are independent, and we prove this statement. Yeah. It's clear? Pay attention, you can find solution in our slides. Okay. It's here. And if you want to print the slides, I add some. I fix it. Now, if you press Ctrl P, you can print all slides on A4 and you will see it's in correct form if you want to print. You can save it as PDF and you can print. So my advice, if you need to solve some question and sample space is small, and you can draw it as a table on some other way, draw it, because it's very intuitive. You can see what's going on, and you don't need to imagine it. But in general, if you can't draw, we need to solve more complicated rules. As I remind previously, for example, here we can use generating function. Okay, it's clear. Can we continue? Okay, it's simple question. Let's make something less simple. Yes. Prime numbers. Do you like prime numbers? But they are very important in combinatorics. They fit in number theory. A mathematician from number theory studies prime numbers, and we want to use them today as our guest for this question. Okay, let's understand the question and try to solve it. Omega sample space is a set. Is a set of p numbers, 1, 2, 3 until p. And we know that p is a prime number. What is a prime number? It is every number that's greater than 1, that has no positive divisors other than 1 and itself. For example, 2, 3, 5, 7, 11, 13, and these are prime numbers. Yes, 2 is only one even prime numbers. You know, there are infinitely many prime numbers, and they're useful in mathematics. Okay, so what we want to check, what we want to prove. Okay, we have sample space of size p, where p is a prime number. Okay, our sigma field is the richest one sigma field, is a set of all subsets of omega. It's the richest one, it's a power set of omega. And for this sigma field, we define probability of every event A as size of A divided by P. That's all. For example, probability of this set equals size of this set, yes, divided by P. 3 over P. Yes? Okay. And what we want to prove? We want to prove this statement. If we have two events, any two events, A, B, and they are independent, one of these statements is false, then at least one of A or B must be either empty set or omega of sample space. So this statement will, if A and B are independent, or A empty set or A sample space, or B is empty set or B is a sample space, or both. Yes.
In this question, what we need to prove is like the definition of independent.
No. It's not definition. We don't say this stuff. We don't say that if A be independent, then A must be or empty set or sample space. No. We need to use definition of independent, but we need to prove this statement.
So we need to use definition to prove this
Statement. Yes, it's enough. Okay, it's enough to use definition.
Like independent probability or.
We will use the first one. We will use this definition. Probability of A intersection B equals probability of A times probability of. We will use this definition, but you can also use this one. We will use this definition to prove this statement. Yes.
Yeah, just we said the probability of the event A is the power set of A.
No, size of A.
Size of A. Okay, that makes so much sense.
Yeah.
The size of A.
It's okay, it's clear. Okay. It's not very important question probability. It's a question for exercise. Yes, it's not so important. But it's good because we use here our guess prime now. Okay. So let's start. Again, you can find solution here. Yes. So show next step, but let's solve it together. Okay. No. Let's take this guy and put it here. Okay. So what we know, what we want to prove. We know that A and B are independent. Yes? So we know the probability of A intersection B equals probability A, probability B, product probability. Okay, let's start from this point. Okay. What is the size of A? We don't know, but we can give him a name. X, N. Yes, M, N. Yeah, that's denoted by N. Okay. What is the size of B? M. We don't know. General, yes. And what is the size of A intersection B? We also don't know. No, we don't know. Let's see. Pay attention. We know that C less equal M. We know that C less equal N. Yes? Because it's an intersection. But we don't know exactly what is the size of intersection. We say smaller? C smaller than, yes. What we know, let's write it. What we know about N? What we know about N? It's greater equal 0, yes?
It's bigger than 10.
And less equal? Yes. M
What is P?
is the size of sample space. Sample space size is P, prime number, and A is event. Size of event also less equal than size of sample space. Yeah? It's subset of omega. So its size must be less equal. Okay. We also know that M between 0 and P. And what we know about C at greater equals 0, yes? It must be less equal P, but also it's less equal M and less equal M. Yes? Minimum. Yeah. So this is our starting point. And now we can start to solve the question. We need to use, we don't need. It's enough to use this equation. Okay. Let's start. What is the probability of A intersection B?
C over.
Yes, C over P. By definition of probability measure this question, probability of any event equals size of this event divided by P. So probability of A intersection P is C. Let's write it here. Probability, just a moment. Probability of A intersection B equals C over P. And we know it's given that equals probability of A. It's N divided by P times probability of M. It's M divided by P. So we have this equality. Make sense?
Yeah.
Okay. Now we want to do it easier. Can we multiply both sides by P?
Yeah.
Why? Probably P is 0. Or P can't be 0.
No, P is a prime number.
If, excellent. Yes, P is a prime number, so we can provide it the next thing times P both sides.
But
Yes,
אנחנו נותנים לנקודת ההנחה שאפס זה לא מספר...
it's fact. Zero is not prime number.
אז הוא זוגי?
No, it's a G, but yes, we'll talk about prime numbers. Yes, it's yeah. Okay, let's find product by P squared.
This exercise, we don't have to prove that P is not 0 because this is the definition of the
Prime numbers, yes. Yeah, also 1 is not prime number.
No, I didn't mean that the P is a prime number. I meant that
But-
this is the definition of the probability here.
Okay, but
You can't keep the
but in general, if you have equality
yeah.
and you have ratios and you want to multiply it by denominator, you need to say something about it. Probably it's 0. So okay, and we get C times P is a prime number equals N times N. Okay, we're here, and P is a prime number. Make sense?
Yeah.
Okay. And what we remember also that N less equal P greater equal 0, and M less equal P greater equal 0. It's enough. Okay, now we need to use some statement from antique statement from Euclidus. P is a prime number, yes? And what we can, okay, the left side divides by P, yes? Also, right side divides by P because it's equality. And now we use famous statement. Okay, it's a joke. Well, why is famous? You probably don't know it, yes, but we were going to use famous statement. If the product, it's a product, yes, of two numbers divided by prime number, products of two numbers, at least one of them must divide by P. We know that this product divides by P. And P is important, is a prime number. From this we can conclude or M divided by P, or M divided by P, or both. It's very important that it's a prime number. Pay attention. If P is not prime, it's incorrect. For example, 4, yes, 4. No. Okay, for example, 4. Okay. It must work. Okay. 4 equals 2. Yes. 3 equals mn. It's incorrect. But 2 divided by 4. It's also incorrect but 2 divided by 4. But it's okay. Why? Because 4 is not a prime number. But if here we get prime numbers, we have prime number, for example, 7. And here we have, for example, I know 49 times 13. In this case, if we know what this guy divided by 7, at least one of them divided by 7. So what we know, or n divided by p, or n divided by p, or both. But what we know about n? It's less equal than p. How can it be that n less equal p and n divides by p? Only two cases.
Or P equals 0.
Or n equals 0, in this case A is empty then, or n is p. In this case, A is a sample space. Similarly for B. That's all. Okay, let's look on the slides. To conclusion. Okay, just a moment. Let's read it together. Okay. Okay, so we are here. Cp equals m times n. By Euclid lemma, if prime p divides a product m times n, it must divide at least one of them, or m or n. But we know that m between 0 and p, we know that n between 0 and p. So this statement is correct only if a equals 0. In this case, size of a is a 0. In this case, a is an empty set. Or size of a is p. In this case, a is a sample set. And similarly for b. This is solution. Is it hard? Is it easy? It depends. It depends. It's not very easy because you need to know something about this lemma, yes?
Yeah.
Oh.
Famous.
Yes, it's famous, but it depends. Yes. Okay. It's clear? Okay. Okay. This is a bad guide for today. Random variable. Okay. The problem with definition of random variable, because it's not intuitive. And the second problem, at least for me, and yeah, I think you talked about with Uri about it, it's confusing. Random variable is not random and it's not variable. It's a function of something. So it's not random, it's not variable. Okay, random variable is a function. Okay. Usually in our course and many books and courses, we denote random variable by capital letters, for example, x. And random variable x is a function that give us for elements from omega, from sigma field of omega, real numbers. It's a function from omega to real numbers. But it's not exact definition, because we can use here any function. The problem is not any function is a random variable. This is the problem. There are infinitely many functions that are random variables, and also these are infinitely many functions that are not random. Okay, so you can use here any function. We need to use here measurable function. Okay, what does it mean, measurable? Good question. But pay attention, it's not theorem, but from experience, yes, from experience of many people. Let's say almost every interesting function you can imagine or you want to use is a measurable. It's very hard to think, to use, to invent some unmeasurable function. So in general, not in mathematics, but in our experience, yes, in general, almost every interesting function is measurable. Sinus of random variable, cosinus, minimum, maximum, products, logarithm, almost everything is measurable. But anyway, there are infinitely many functions that are not measurable. So we need to give exact definition. Okay, when we say that function is measured, okay, this is definition, and we have question to check the definition. We have one exercise about it. We say that x is immeasurable if for every real number x, this statement holds. So what does it mean? For every x, this set belongs to sigma 3. Okay, what we need to understand this set. Okay, this set has every omega such that x of omega, our function x for omega, give us a number z less equal to x. We need to check it for every. If this is the case, we can say that we have random variable. If not, it's not. Again, as I said, almost every interesting function that you can imagine or you can see in your work is measurable, but there are infinitely many unmeasurable functions. And now I will show you example. We will do exercise and you will see examples of measurable function and unmeasurable. But in practical way, for example, if you work as data science, almost every function will randomly.
So almost every function is a random variable.
Almost very interesting function that you will see in your work is a measurable. But in theoretical way, there are infinitely many measurable functions and infinitely many unmeasurable.
What is unmeasurable function?
The function that this statement is incorrect.
Do you have an example?
Yes, next exercise. Yes. But usually it's something very not common and not very practical. But in mathematics, we can define whatever we want. Yes, so we can define measurable. Yes, I give you example, but it's not something interesting. Yes. Usually it's something messy and something with not common. Yes. Okay. So this is definition. And now let's do exercise. Okay, it's exercise number 5, no, it's 6. Okay, yes. Okay, it's not very important exercise, but it's important because in this exercise we will see example for measurable function and unmeasurable. Yes. Okay, let's look at this exercise. This is 2 examples. We have sample space with 3 elements A, B, C. And we have sigma algebra. It's a not power set of omega. This is sigma algebra. How many elements it has? 4. Yes, 1, 2, 3, 4. You can check this is sigma algebra. C is here, complement of C is here, empty set is here, sample space is here, any union of these 2 guys is here. This is properly defined sigma case. Okay, pay attention, we even don't need probability function for this question. It's not necessary because we won't calculate probabilities. So probability function is not given. What we have here, we define here three functions. X, Y, Z. It's not a variable, but it's a function. Okay? X, Y, Z. These functions are from sample space to real numbers. Okay. X for A gives 0, for B returns 0, for C we have 2. This is function. The question is, does it measure? Is it measurable? Yes. Why? For A, we have 1, for B, we have 2, for C, we have 2. Is it measurable? And similarly, we have here 3 functions, and we want to check which one of them is a random variable, is a measurable, and which one of them is not. That's all. It's a question of definition, but it's important to see examples of measurable function and unmeasurable. Okay, the equation is clear. Okay, let's make copy paste and try and start to solve. Okay. But pay attention to the artificial question. Yes, it's not something practical. Okay, let's start. Yeah.
The small x need to be less or equal to 7?
7? Why 7?
Because omega e is 7. I don't understand what is.
No, omega is ABC.
Yeah, but the definition said that.
Let's take definition. Okay, where is it? Where is definition? No, not.
Omega is smaller than small e, so I don't.
Yes. Let's copy paste it. Okay. Just a moment. Yeah, it's here. Let's take it. Okay. Let's see. Okay, so this is definition, this is our data. Okay, let's check if x is a random variable. Okay. Pay attention, we need to check this statement for every x, yes? Okay, but what is the values of x? It's 0 and 2. Yes, x has get only 2 values. 0 and 2. Again. Zero and 2. Okay, 0. So we don't need to check here infinity x's. It's enough to check some x, to choose some x between infinity minus infinity to 0, some x between 0 and 2, and some x greater than. So we have only three intervals to check. Okay. Let's start to check. Suppose x, just a moment. Okay, suppose x is a some number that less than 2. Sorry, less equals 0.
This is small.
Yes, small x, yes. Just a moment, you're right, yes. It's something with this program, I need to check it. Okay. Okay. It's a small x. Oh. What is the probability? Sorry, not probability. What is this set? Is it belongs to F?
No.
Yes, it's an empty set. Why? We want to find here omega, such that x of omega less equal some number that.
But you want it's less than equal.
Less equal, yes.
0 is
Okay, but I need less. You're right. Yeah.
So without
0, yes.
not it.
Yes, you're right. Okay, you're right. Without 0. No. Okay, without 0. Okay, yes. Just okay, yes. Oh. So it's empty set. Only for this set for x less than 0 is empty set. Let's try it. For sets, I need to use another other program. Okay, so this set. Just a moment, I want to use something else. Okay. Let's use this guy. Oh, this set of omega from capital omega such that x of omega less equal x and x less than 0 is empty set. Yes. Is empty set belong to sigma field? Yes, it's by definition, yes. It's a member of A. Okay. Now we choose x greater equals 0 less 2. And let's find out this set. Alpha omega belongs to capital omega such that x of omega less equal x and x between 0 and okay, look on this column. For every x in this interval, this set equals AB. AB. And the question is if AB belongs to F. We need to check, yes? Okay, where is it? If AB belongs to F, yes, it's given. It's a member of F. Okay, so it belongs to. And the last case, x greater equals 2. In this case, we set equals for omega. Yes. Just a moment. I need to remove this handwriting. Oh, if x greater equal to, we set equals a, b, c. It's a omega. It belongs to F by definition of sigma field. It's given. Okay. For every x from R, this statement holds. So x is a measurable. So x is a random variable. X is fellow random variable.
So a little confused. So how did you find, like, for example, we said 2 is less than or equal to x. How did we get to the A, B, C? Like,
Okay. Look, we need to check this statement. Let's choose some number. X equals to 3. X equals 3.
yeah.
We need to find sets of omegas, yes, such that x of omega less equal 3. For example, yes?
Yeah.
Okay, let's check. X of A less equal 3. This is x of A. Less equal 3. X of A, it's 0. It's less equal 3. So A belongs to the answer. X of B less equal 3. 0 less equal 3.
Oh, yeah.
Yes, so B also belongs to the answer. X of C less equal 3. Yes. So the answer here we set here is A, B, C. It's a sample space.
Okay, so all 3 omegas are.
Yes.
Yeah, fine.
Okay. And now let's check your intuition here in Y for Y. Okay. Let's check your intuition here. You will help me if you want in Y. Okay. Let's please help me for Y. Okay. So X is a random variable. It's measurable. Let's check Y. And please, if you want, help me. Okay. Just a moment. Let's remove this. Oh. Okay, let's start. Y of omega. What is the value of Y? 1 and 2, yes? So here we have 3 cases. Y, small y, less 1. Y great equal 1 less than 2. And again, y great equal. Why? Because y get only 2 values, 1 and 2. And now please help me find out this set, and this set. Okay, let's start from this guy. The sets of omega such that y of omega less equal y. And now if it's confusing, choose any y you want from this interval. 0. Please look on this column. And what is this set of omega such that y of omega less equal 0? When y of omega less equal 0?
No one said.
Oh, never. It's empty set. So here, empty set. If it's a member of F, if it's in sigma field, yes, it's given, and this is a property of sigma field. Okay. Now we want to check this value. W omega such that y of omega less equal small y. And again, you can choose here any one in this interval, 1.5. Okay, let us think about this value. Y is 1.5. What is the length from omega such that y of omega less equal 1.5?
Easy.
Less equal 1.5.
Only eight.
Only 8. So this set is 8. And the question is, it's a question, is it a member of sigma field? Let's check.
No.
No, we don't have this fellow in sigma field. That's all. It's not, y is not a measurable function. Y is not a random variable. That's all. So this answers to your question. But it's, it's not very clever example. It's a technical example, but here y is not a random variable. In this sigma field, for other sigma field, it can be a random variable. But for this sigma field, it's not a random variable.
You can intersection in the sigma field is you can get A. So
Okay, but you need to extend this sigma field. For this sigma field, it's not. You can take this sigma field, add some elements, and it will random variable.
It have to be one of the atoms.
Yes.
You mean?
But also we don't check this field. Probably we need additional.
Yeah, we don't have it. It's very confusing because you can generate every subset of omega, for example, the singular A, with those atoms.
Yes.
But it doesn't matter on this exercise because it have to be one of the lists of atoms.
And if, for example, we'll have this guy in a sigma field A, we need to continue our investigation to the next step. It's a good example, and here, as you can see, this guy is not random variable. This one is yes. Let's check the last one. Let's use slides. Okay, just a moment. Okay, we are not here. Here, yes, okay. Okay, yeah. Okay, we do this work for x, we do it for y, sorry, and we see that it's not random variable, and the last fellow also, z is not random variable. If we check for every x less than 1, it's an empty set, you can check it, it's okay. But after that, we check, we have interval from 1 until 4, and for any number here, we will get again A. And we said A is not the subset of sigma field, so also Z is not a random variable, similarly. Okay, make sense?
Yeah.
Okay. We continue. There are many interesting exercises here. We will continue with these notes next time. Okay, let me say a couple of things and we will stop. And also let's check a message from Ori. Probably Ori will be late. Let me check. Just a moment, I asked him. Probably I call him. If I couldn't, let's ask him. Okay. Okay, I published solution for homework 1. If you find some error or something not logical in solution, tell me, I repay it. Okay. I published today homework number 2. I published homework number number 3 today, sorry, number 2 previous time. Pay attention, the homeworks are not easy. There are many exercises, but it's for you to study. As I said previously, you can solve some of exercises without any help, with lecture notes and recitation notes. For some of the questions, probably need to ask ChatGPT for advice or for tip. It's okay. And try to solve the maximum question that you have from any homework, because this is your way how you study, okay? As usual. And you will get feedback, but it's a partial feedback. Not everyone will get feedback for every exercise, in addition to solutions. And if you have any question, you can ask me now, or you can send me email and we can rearrange a Zoom reception hours. Okay? Any question before we stop? Let's check. Yes, just a moment. Yes.
Question about the prime number before you mentioned.
Prime number?
Maybe I missed something you said. Why we cannot choose M and N to be one of them is 1 and one of them to be P.
If one of them is P, it's okay because it's sample space. Just a moment. It's next question. Yeah, it's here. Okay, yes. M or N must divide by P. So M or N must be or P or 0, not 1.
If we have C is 1, P is P, and M.
C does not matter in this game.
Huh?
Okay, but you can assume it's 1, but it does not.
The P, M, and N.
C is not important for solution. It does not matter, yes.
But if
P is a prime number. It's 2, 3, 5. Okay.
But if P is if M is 1, M is P,
Or
it also can match this form.
no, it's okay. If N is P, is okay.
But then it doesn't meet the.
What we want to prove? We want to prove that size. Okay, just a moment. We want to prove that A is a sample space or empty set, or B is a sample space or empty set. This is our statement. If N is P,
How?
then B is a sample space. It's enough. It's enough. Okay, makes sense now.
Okay.
Yeah. Some additional question? Yeah.
So just for problem 6.
Problem 6. Just a moment.
I think what I'm a little confused about is where are we getting the x's from? Because I was kind of thinking that the small x was any real number.
Yes.
And we're just checking any real number to see if we can, but we're kind of not. We're using like x can only be, we said.
Just a moment. Yes, I won't write it. Okay, pay attention. This is values of, yes.
Yeah.
So x, we divide a, okay, x is any real number,
Yeah.
but we have 3 cases to check. It can be any real number below 0. It can be any real number between 0 and 2, or any real number greater equals 2. So it can be any real number, but we have 3 cases to check. And we check, and we see for this case, and for this case, the definition holds. So we conclude that x is a random variable. Yes? Okay. Okay, let's check Uri. Just a moment, I'll call him and ask him, is it going to wait? Just a moment. If yes, I talk you to do something probably. Just a moment, let's talk with Uri. Okay, it's busy. Okay, it's busy now. Anyway, okay, so thank you. We will stop here. And if you have questions, you can ask me now. We have a couple of minutes. I'm here. If not, send me email, okay? Thank you very much.
Thank you.